In this video, we're going to solve two closely related problems. So we're basically going to go backwards, and given the percent dissociation of a weak acid, we're going to work back to find the acid dissociation constant. And then I'm going to do a similar problem where we start from the pH and find the Ka value. So let's see how this works. I'm going to start from an ice table again, just so I can kind of understand what's going on. So let's always start by writing the dissociation for the acid. So there's our lactic acid breaking down. We don't know the Ka this time, right? This is what we're looking for. But if we kind of just picture what's going on in terms of equilibrium, set up our ice table to help us visualize the problem, then we know in this case we started with a 0.1 molar solution of the acid, none of these. X amount breaks down, and so we get X amount of each of these. And so at equilibrium, this would have been 0.1 minus X, X, and X. The problem is we don't have any numbers, or at least we don't seem to. Here's the important point. We are told it's 3.7% dissociated. In a previous video, we saw that the percent ionization, or percent dissociation, is just X, the amount of hydrogen ion, for example, or basically the amount of acid dissociated at equilibrium over the original concentration of the acid, which we'll symbolize with that with a sub-zero, right? So we know that this must be equal to 3.7%, which means it equals 0.037, once we take the factor of 100 out and turn this into a decimal. What does that tell us? Well, it tells us basically what X is, because if you solve this for X, you just take this percent of the original concentration, right? Which in our case is 0.037 times 0.1 molar, and of course that's just 0.0037 molar. But how does that get us Ka? Well, once we know X, we know all the other parts, right? We know basically all the concentrations at equilibrium. So now if we write our equilibrium expression, it's just going to be X times X over 0.1 minus X, which is just going to be X squared, right? I'll just write it out the long way. But basically it's X squared, and then it's over 0.1 minus 0.0037, and we can just evaluate that and see what we get. In this case, I get about 1.42 times 10 to the minus fourth for the value of Ka. So again, just a quick summary. The reason why this problem is a little different than the last problems is that we're going the other way. We still use a basic ice table, we still use the basic equilibrium constant expression, but starting from the percent, we have to remember what this relationship means, this percent ionization, okay? And that's what allows us to get the equilibrium amounts of everything to plug into the expression. Now, we could come at this again from a very similar way if instead of the percent ionization we knew the pH. So let me kind of scroll down here to a kind of a similar problem. Here we're using the generic weak acid model, so I'm just going to call it HA, and that just breaks into H plus and A minus, okay? We're going to start again the same way just to kind of visualize how the problem works. So we have an initial, a change, and an equilibrium amount. This starts as 0.12 molar, 0 and 0. X of this dissociates, giving X of this and that. And then it's 0.12 minus X, X, and X. Now, remember that pH is the negative log of the hydrogen ion concentration. And conversely, if we want to find the hydrogen ion concentration, we do 10 to the minus pH, right? Basically the inverse log. Remember, these are base 10 logs. But if I find the hydrogen ion concentration, isn't this also the same thing as what we're calling X, which is this? And then once again, once we find that, we can plug everything back into the equilibrium constant expression and find our value for Ka. So let's just go through the process here and we'll figure that out. So let's see, I need to take 10 to the minus 3.26. So my hydrogen concentrate, oops, slipped up there. My hydrogen ion concentration, which is my X, is just 10 to the minus 3.26, which is about 5.5 times 10 to the minus fourth. Okay, so if that's X, then I can write 5.5 times 10 to the minus fourth, again, times X again, so it's just squared, but I'll write it out the long way in case you're looking and you're confused why that suddenly got squared. And then I put that over 0.12 minus 5.5 times 10 to the minus fourth. Now, you can type that all in, but for the most part, that 5% rule kind of matters here, or I guess it doesn't really matter, but it makes at least simpler. If we ignore that little bit subtracted, it won't make a difference, but I'll just write it out the long way and see what happens. So this is squared, and I divide by the quantity 0.12, and I'll even subtract just to make you happy, times 10 to the minus fourth, just for the sake of argument. And I get about 2.5 times 10 to the minus 6 for the equilibrium constant. Okay, the Ka for the acid dissociation constant. So again, we came at this from two different places. In one case, we did it using percent ionization, and that allowed us to find the equilibrium amounts of everything and plug them into the K expression. And then we did the same thing, but starting from pH.